Dear students, today we will have the first session on galvanic cells. As you all know, galvanic cells is an arrangement by which electrical energy is tapped from a redox reaction. Redox reaction is a reaction in which oxidation and reduction takes place simultaneously. Now, here I have given a reaction which is a redox reaction in which you can see both oxidation as well as reduction taking place simultaneously. This is a zinc rod dipped in copper sulphate solution, and you can see that the copper has been displaced by zinc to give metallic copper, and zinc takes the place of the copper. It becomes zinc sulphate, which will be a colorless solution. Now, let us see what is happening here. The zinc becomes zinc sulphate, means zinc gets oxidized to Zn2 plus. The oxidation state is Zn2 plus, while copper, which was in the +2 state, oxidation state, gets converted into the 0 oxidation state. Now, here this is a reaction, a redox reaction, which takes place directly when zinc is in direct contact with copper sulphate solution. Now, this technique, we are going to make this reaction take place in an indirect way in a cell known as galvanic cell, where the electrons, they are being pumped throughout the circuit through an external wire, and the flow of electron through an external wire is the flow of electricity, and this setup is known as a galvanic cell. So, let us see what is the definition of a galvanic cell. An electrochemical cell or a galvanic cell or a voltaic cell is a device in which chemical energy is converted into electrical energy as a result of an indirect redox reaction taking place within the cell. So, that is a galvanic cell. Now, let us see an example for a galvanic cell. So, here we have a zinc sulphate solution taken in a beaker, a zinc rod dipped in the same zinc sulphate solution. Then we have another solution which is copper sulphate, which is shown in this blue color, and a copper rod dipped in it. Now, here the zinc and copper sulphate solutions are not in direct contact, but we have an external wire connected to it, and here we place a voltmeter to detect the flow of electricity, and it is connected to a copper rod. So, it is not directly connected, but through an external wire. Now, let us see what is happening here. Here what happens is, when zinc is in contact with zinc sulphate, zinc in contact with zinc sulphate, that is, I am putting it in the bracket, that is zinc sulphate solution. Now, what happens is, here the zinc tends to lose its electrons, forming Zn2 plus ions plus 2 electrons. These 2 electrons, they move up through this external wire, reaches the copper rod. Now, what happens there? There we know that here the copper ions are present in copper sulphate solution. Okay. Here this copper ion takes up 2 electrons from this electrode, then gets converted into the neutral copper metal. So, the electrons are arriving from zinc to copper through the external wire, and copper gets the 2 electrons, gets reduced to copper metal. Now, you can say that is an oxidation taking place here. Here we have an oxidation, and here we have the reduction reaction taking place. In short, there are 2 half parts of the cell, or you can call it as half cells, which is known as electrodes. They are known as electrodes. Okay. And the electrode at which oxidation takes place is known as the anode, and the electrode at which the reduction takes place is known as the cathode. And remember, this anode and cathode does not have any connection with the sign of the electrode. So, the electrode at which oxidation takes place is the anode, and the electrode at which reduction takes place is known as the cathode. Now, here in this figure again you have noted another thing that is known as a salt bridge. Now, in this galvanic cell, you can see that here the zinc is coming out as zinc ions, okay, and this zinc ion does not have any sulphate ions to neutralize its charge. So, here there will be an accumulation of positive charge. Here positive charges like it will be accumulating here, and in the case of copper sulphate solution, the copper ions are getting discharged as copper. So, the sulphate ions are left out. In short, you can see that the anodic solution is getting positively charged and the cathodic solution is getting negatively charged. So, what happens is more and more zinc cannot come into solution. Here copper ions cannot get discharged as copper metal. Now, this accumulation of charges is prevented by an arrangement known as salt bridge. See, here it is the salt bridge. It is a U-shaped tube which is filled with KCl and agar-agar gel. Now, salt bridge, what it does is it prevents the accumulation of charges by allowing the flow of charge through it, and therefore, the charge gets neutralized, and you can have more and more zinc getting oxidized and copper getting deposited, and thereby the flow of current is continued. At the same time, it does not allow the connection, direct connection between the two electrolytes. So, we need a salt bridge in order to facilitate the reaction to prevent the direct reaction between the two electrolytes, as well as for the smooth functioning of an electrolyte. Now, let us see what are the functions of an salt bridge. Salt bridge is an U-shaped tube containing a concentrated solution of an inert electrolyte, like you can use KCl, potassium nitrate, ammonium nitrate, any of these, mixed with an agar-agar gel, so that it becomes a gel type solution. And the main functions are, it completes the electrical circuit in a galvanic cell, as we have seen, otherwise there will be charge accumulation. It prevents the accumulation of charges in the two electrolytic solutions. It allows the free migration of ions through them, and it prevents or it gives an electrical neutrality in the two half cells. Again, it prevents the mechanical mixing of the two electrolytes, otherwise once the cell is set up, you will have to keep on changing the electrolyte. So, it prevents that too. So, these are the advantages of an salt bridge. Next is Daniell cell. This is a Daniell cell, it is a electrochemical cell or a voltaic cell which has been developed by English chemist John Frederick Daniell. Here there is one difference with the cell which we have mentioned before. Here the electrolytic solutions, they are not separated by a salt bridge, and it is separated by a porous diaphragm, so that the zinc ions or the sulphate ions, they can migrate to either side. We have told that in the anodic solution we have the accumulation of zinc ions, and in cathodic solutions you have the accumulation of sulphate ions. These sulphate ions can migrate towards the anodic solution and neutralize the zinc ions, and therefore, the electrical neutrality can be kept because we are having a porous diaphragm. Now, here the difference is that you will have to keep on changing the electrolytic solution, because the copper solution, copper ions will be completely getting consumed, and you will not be having the copper sulphate solution for a longer time. So, that is the difficulty in such solutions, and this is the first cell, Daniell cell, voltaic cell which was discovered by Daniel. Now, how will you represent a galvanic cell? Here a galvanic cell, you can represent it like, you should first put anode on the left hand side and cathode on the right hand side. Okay. So, that is a way. So, when I put a galvanic cell, I will be writing first anode and then I will write the cathode. As we have mentioned before, anode should be that electrode at which oxidation is taking place, and cathode should be the electrode at which reduction is taking place. Now, let us consider the first cell which we had told in the beginning. So, here we have anode as zinc rod digged in zinc sulphate solution. Now, you can see that the zinc rod as well as the zinc sulphate solution, both are two different phases. So, in order to separate them, we usually represent it with a bar. Okay. Similarly, the copper in contact with copper sulphate solution. So, here I am going to put this as zinc in contact with zinc sulphate solution, because these two are two phases and they are separated by this bar. Now, on the other side we were having copper and copper sulphate solution, but you know that the cathode we will have to represent it as, we will put copper sulphate solution first and then copper. This is because we know that these two solutions are in contact either in an indirect way or by a porous diaphragm. In the first mentioned cell, we were using a salt bridge. So, we have to represent it as a double bar, which shows that these solutions are not in direct contact. In Daniel's cell, there was a difference, that we have zinc rod in contact with zinc sulphate solution, but here we have been using a porous diaphragm, which is shown by a broken line. Then we have copper sulphate solution and then copper, and the external circuits are from these two metals. So, solutions are together, both the electrolyte, that is anodic and the cathodic electrolytes are put together, and we have either a salt bridge or a porous diaphragm. When we use porous diaphragm, we call that cell setup to be the Daniel cell. The other one is generally a voltaic cell, in which these two solutions are separated by a salt bridge. Okay. So, this is how we have to write a cell. This is how we will be representing a cell, and whenever a cell is represented, the electrode shown on the left hand side will be the anode. We will not be mentioning it as an anode, but you should understand that the electrode which is shown on the left hand side is anode, and that which is shown at the right hand side is the cathode. Okay. So, in this class we have been dealing with galvanic cell. As we have seen, it is a setup for deriving electrical energy from a redox reaction taking place within the cell. Then we have been seeing a galvanic cell, an example where zinc rod is dipped in zinc sulphate solution and copper rod dipped in copper sulphate solution, and these two connected by a voltmeter to show that there is a flow of current. Then we told about an anode and the cathode. Anode is electrode at which oxidation takes place, and cathode is the electrode at which reduction takes place. It has got no relation with the sign convention. And we see the salt bridge. Salt bridge is mainly to have the electrical neutrality between the two electrolytes and have the smooth running of the galvanic cell. Then we have seen a Daniel cell, which was a first galvanic cell which has been devised by Frederick Daniel, and here we saw that both the solutions are together separated just by a porous diaphragm, and this porous diaphragm you can see that the ions move directly, and therefore, the electrolyte has to be replaced after a certain period during the working of an electrolytic cell. And we saw that a galvanic cell can be represented in an easier way with zinc in zinc sulphate solution, which represents the anode, separated by a double bar that represents the salt bridge. That is, whenever you use a salt bridge, you have to put a double bar. Then we have the cathodic solution and then the metal. In the case of Daniell cell, since we have only a porous diaphragm, it is shown by a broken line, that is zinc in contact with zinc sulphate. Here we have a porous diaphragm, then we have the copper sulphate solution and copper. Today we have been seeing galvanic cells, anode, cathode, an example as Daniell cell, which was the first galvanic cell devised, representation, how can a galvanic cell be represented. So, with that we conclude today's class. Thank you.